In Chapter 3, we're going to look at systems of equations, and this is something that you've studied in the past, and there's different ways to solve systems. Today we are going to look at solving systems of equations by graphing. And if you are a tennis fan, you might know this man is Andre Agassi. If you can figure out who this woman is, then maybe you'll get the joke. So the first question is, what is a system of equations? Well, a system of equations is basically just if I have more than one equation. So I might have, these two equations, I have this bracket out front, that would be a system. And really a system is a compound sentence joined by the word and. So if I were reading this, I'd say, okay, well, y equals 2x minus 7 and y equals negative 3x plus 1. So if I want to find the solution to a system of equations, I would really want to find the values, or in this case, the coordinates x and y that make both equations true. This is the key. If I want the solution to a system, I need to make both equations in the system true. So what we're going to look at today is graphing. There's kind of three different situations that may arise. If I'm graphing lines, it's possible that maybe, I don't know, I'd get something that looks like this. If I'm looking off of a graph, the solution to a system then would be the point where the two lines cross. So this is the point that both equations would have in common, that both lines have in common. That's the solution to the system. So here it looks like maybe my solution is at that point 4, 6. I could also graph lines that are parallel. And where would these lines cross? What points do these lines have in common? Well, if they're parallel, these lines actually aren't going to have any points in common. So for this system, there is no solution. The third case is maybe I graph a line and then I look at another line and it's the exact same line. So maybe the lines have the same slope and the same y-intercept, they're the same line. Then what would the solutions be? Well, if I have two lines that are the same, there's an infinite number of points that these lines would have in common. So here, there would be infinite solutions. And really, what that infinite solutions means is any point on the line is a solution. So infinite solutions, any point on the line is a solution if the system contains two lines that are the same line. Now, just a caution, sometimes I get students that say this, do not say infinity. So infinity is not a solution. I'm saying just there's an infinite number of solutions, they aren't countable. So let's look at an example. If I want to find the solution to the system by graphing, let's look at my system over here. This is in slope-intercept form, so I could graph that pretty easily. My y-intercept is at 0, 10, and then my slope is negative 3/2, so I'm going down 3 over 2, down 3 over 2. So graphing that first line is pretty slick. The second line, think about what form this is in. The second line is actually in standard form. So if you wanted to, you could solve for y, but if I notice, 4 and 8 both go into 16, so if I leave it in standard form, I could just find my intercepts. So if I want to find the y-intercept, I'm going to plug in 0 for x. If I plug in 0 for x, this would go away. I'd be left with negative 8y equals 16. Y would have to be negative 2. So that's the y-intercept. If I want to find the x-intercept, I could plug in 0 for y. So to find the x-intercept, plug in 0 for y. If I plug in 0 for y, now this second part would go away. So 4x equals 16. 4 times what is 16? That would be 4. So that's the x-intercept. And since I have 2 points, I can go ahead and graph the line using those 2 points. Or maybe you would have preferred to put this in slope-intercept form. If you put it in slope-intercept form, you maybe would subtract your x, divide by -8. If you divide each term by -8, in the end you should end up with something like this. So either I can graph using my intercepts, 0, -2, 4, 0, or I could use slope-intercept form, solve for y. So start at 0, -2, go up 1/2, same line either way. Now where is the solution to the system? So the solution is the point that both of these lines have in common. And maybe you guessed it, here it is. The solution is right there at the point 6, 1. Now, how could I check that my solution is correct? Well, I could plug in 6 for x and 1 for y back into the original equation. So if I take 4 times 6 minus 8 times 1, I'm going to get out 16. Also, if I take -3/2 times 6 plus 10, I should get out 1. So if I plug in this point 6, 1 into both equations, it should make the first and second equation true. Therefore, 6, 1 is a solution to this system. So at this point, here's another example. Maybe pause the video and attempt to find the solution to this system. So pause the video at this time and give it a try. Now, I'm not sure how you approached graphing these, but I'm noticing that the first line is in point slope form. And it looks like the point from point slope would be, it looks like 1, -6 was plugged in here, x minus 1, and y minus -6 would be like y plus 6. So for point slope form, that point I can see that's on the line is 1, -6. And then the slope's right here, that's the 3. So I'm going up 3 over 1. And there's your line. Oops, let's try again. There we go. Second equation is in standard form. So I don't know if you guys use the intercepts or not. 6 and 2 both divide into 18 nicely. They're both factors of 18. So if I plug in 0 for x, this would be gone. -2 times -9 is 18. So that would be a point on that second line. If I plug in 0 for y to find the x-intercept, 6 times 3 is 18. So 0, -9, 3, 0. Wait a minute, those points, this actually looks like the same line. Now, maybe some of you rewrote both of these in slope-intercept form. If you did rewrite this first line in slope-intercept form, you would get y equals 3x minus 9. If you rewrote the second line in slope-intercept form, you maybe started there, eventually you would have gotten y equals 3x minus 9. And yes, these are actually the same line. So what's the solution to the system? Well, there's an infinite number of solutions. Does this mean any coordinate I pick is a solution? No. I mean, is this point over here a solution to the system? Absolutely not. That point is not on the line. But any point on the line, so if I pick any point in here that's on the line, that's going to be a solution to the system. So an infinite number of solutions. And more specifically, I'm just going to specify any solution must be a point on the line. So any point on the line, as these are actually the same line. So just a follow-up question here. Is the point -2,5 a solution to this system? So just a check for understanding. I want to know if the point -2,5 is a solution to this system. Pause the video and decide whether you think that point is a solution or not. So to determine if -2,5 is a solution to the system, I'd want to plug in -2 for x and 5 for y. So I have done that for the first equation. The work is shown here. And if I go through, does 1 equal 1? Yeah, this is a true equation. But I also need to check it for the other equation. So now I have 4 times if x is -2 and y is 5, does that make the equation true? So for the second equation, I get something like -3 equals 3. Well, this absolutely is not true. So is -2,5 a solution to the system? No. That point does not make both equations true. If I were to graph these lines, it might look something like, I don't know, might look something like this. The point -2,5 would be over here. So that point -2,5 is on the first line. Yes, it's on that first line, but it's not on the second line. So since this point does not make the first and the second equation true, it is not a solution to the system. The solution to the system would actually be somewhere down here. Let's look at one last scenario. So here's a system of equations. The first equation is in slope-intercept form. The second equation, let's just rewrite quickly. So it's in slope-intercept form. So if I divide everything by 3, 12 divided by 3, and -80 over 3, I'll just leave it like that. 3 does not divide into 80 evenly. So, okay, I'm just kind of rewritten. Here's actually the second line. Here's the first line in slope-intercept form. Now, what's the downfall to finding the solution to a system by graphing? Well, if I'm looking at a graph, the solution might not always involve integers. So I might not be able to look on a graph and know exactly where that point of intersection is, especially if I'm dealing with y-intercepts and things that aren't nice whole numbers. So that's where the graphing calculator comes into play. And this is really a big idea, so pay close attention. Grab out your graphing calculator. And if I want to graph on the graphing calculator, you're going to go to the y equals button, which is on kind of the top of your calculator, the top left. If you have any equations after the equal sign, just hit clear. So clear those out. And then we're going to type in our functions. Now careful, if it says the opposite of x, do not hit the subtraction key. You want to actually use the negative button, which is way at the bottom of your calculator. So use that negative button. It's the opposite of, here's your x, minus 8.5. If you do not use the negative key in front of the x, your line won't graph. Then your second line is 4x minus 80 divided by 3. So I've inputted both lines. Now before I graph this, I want to point out, go to the middle key, zoom. Lots of times I'll tell you to do a zoom 6. This is your standard window. So a zoom standard, if you hit zoom 6 and go to graph, The window's going to go from -10 to +10 on the x-axis, -10 to +10 on the y-axis. So that's kind of the default window for the graphing calculators. Now there's maybe a problem here because I can't see the solution. I can't see the point of intersection. So if I want to change the window, go to Window, and you'll notice here it shows me, okay, I can see from -10 to 10 on the x and y axis. This 1 means that there's a tick mark every 1 unit. And if we go back to the graph, well, I really want to see further down on the graph. So I really want to see lower on the y-axis. So it looks like I'm okay left to right. But if I want to see further down, I would want to change the y minimum. So I want to see lower on the y-axis. And let's just go, I don't know, maybe 10 more units below. So hit your negative key again. Let's go to -20 and see if that does it. So now I can see lower on the graph. Sure enough, here's my point of intersection. Now the calculator will actually find the point of intersection for you. So once you've graphed these, you've got your window. This calculate feature here is very nice. It's written above the trace key. So if I want to hit something above the trace key, I need to go to second trace. So second trace will get me that calculate feature. And what do I want to know? Well, I really want to know the intersection. Where do these lines cross? So second calculate, intersect, option 5. And if you notice here, it says first curve. So this allows me to scroll along the first curve. If there were multiple places where these lines cross, that would become useful. Since there's only one place these lines cross, I can just hit enter right now. If there were multiple places the lines cross, I just want to scroll that point kind of to where the lines cross. Here, doesn't matter. You should just be able to hit enter. When it says second curve, again, I could scroll along the second curve, but I'm just going to hit enter. Guess, I don't want to guess, hit enter again. So let me go through that one more time. It's second calc, intersect, choice 5, and then I've really just done enter, enter, enter. I don't need to scroll that cursor because there's only one possible point of intersection. And here's my answer. So these lines cross at 3.63 repeating and -12.13 repeating. So that coordinate is the solution to this system. It's the point that's on both lines. Now I just want to highlight one or two more features. If you go to trace on your graph, you can actually scroll along the functions and it'll tell you the x and y values. You can type something in, so I could type in 0 for x and see what comes out for y. If I type in 3.63333 for x, I should get out, there's my point of intersection. I could jump back and forth between the lines by hitting the up and down arrows. So that would kind of bring me from one line to the other. So that trace feature is kind of cool. Also, there's a table feature. So if you go to second graph, it brings up a table. And it shows you your inputs and outputs. So if I input a number for x, what comes out on the first function for y and the second function for y. So lots of cool things you can do with your graphing calculator.